Hi, and welcome to the problem session for Lecture 11. In this problem session, we're going to discuss more about vectors and matrices, including concepts like linear independence, spanning vectors, matrix rank. Most of all, we're going to be discussing how to use this stuff that we did in the previous lecture to solve systems of linear equations. Okay. I'm going to begin, though, with some of the more basic ideas of linear independence and so on. I'm going to start with writing down a few vectors. Here's A, here is B, and here is C. And the question is, are these three vectors linearly independent? Okay. Now, in general, it can be difficult to determine that. This is a negative 3, by the way. It can be difficult to determine that in general because the definition of linear independence is when you cannot write the any one of the vectors in terms of a linear combination of any of the other vectors. So, for instance, I cannot write A in terms of, let's say, some combination of B plus C for some S and T. So that's so that means the vectors are linearly independent. So to try to figure out whether or not they're linearly independent, you have to show that there's no possible way of writing them as a combination of each other. Now, one way of showing that in general, if you have sort of the same number of vectors as their dimension, is you can put them all in a matrix and take the determinant. If the determinant is 0, you know there's some kind of linearly dependence going on there. However, we don't have the case here, so we have to figure out in a different way whether or not one is a combination of the other. There's no obvious one here in the sense that no one is, say, double or triple one of the other ones, but we can try to guess to see if there's any kind of combination of one that makes another one. There are a couple ways to do this. One, we could actually go through and try to solve a system of equations. Since we do that anyway later on in the problem session, we'll just instead kind of eyeball it and see if we can find any combination. Let's try to write B in terms of A and C in this case because B has bigger numbers. Not very scientific, but it's an approach. So, what if you want to write B in terms of some combination of A and C? Well, B is, the first element is 6, so either we could write 2 times A would give us 2 times 2, and then 2 times C would give us 2, so 2A plus 2C would give us the first element 6. But the second element would give us 2 plus 2, which would be 4, which is not equal to 5, so it can't be 2 and 2. How about 3 and 0? Well, no, because 3 times 1 is 3, not 5, so again, it can't be 3 and 0. Can it be 0 and 6? No, because the second element would then be 6 times 1 is 6 instead of 5. So we can't do that one, so we're pretty much left with one attempt, which is 1 times A and 4 times C. 1A gives us 2, so if we do that, we can see we get 2 plus 4 times 1. That works. That's 6. And then we get 1 plus 4 times 1. That's 5. That works. Then we get 1 plus 4 times negative 3. That's negative 12 plus 1 is negative 11. That works. And then negative 1 plus 4 times 4 is 16 minus 1 is 15. That works. So it turns out this combination of A plus 4C gives you B, and these vectors are not linearly independent. Now again, there's some guesswork in there. We guessed that we can write them in terms of B. There are many different ways you can write them. You can write them in terms of A. You can write A in terms of B and C or whatever. They just give you different equations. But in general, what you're trying to do is figure out if there's some combination of these of two vectors that make a third by choosing appropriate values of the coefficients multiplying the vectors in the linear combination. So in this case, we find that we do not have 3 linearly independent vectors. We have 2 linearly independent vectors. Do we have only 1? No, because we can't write any 1 in terms of... So in this case, we get rid of B, but we can't write A in terms of C, so we're left with 2 linearly independent vectors. Next question we can ask are what's the size of the space they span? Well, they have these have dimension 4, so they could in theory span dimension 4. If there are 4 of them, they're linearly independent. There are not 4 of them, so we can't do 4. We could at most do a 3-dimensional space to span. However, since you create B in terms of A and C, you would most have 2 linearly independent vectors, which means they can span at most a 2-dimensional space. So there you go. There's an example of that. Next few examples are all going to be, actually all the next examples are solving systems of equations. I think we have one question about matrix rank somewhere in here, maybe, or maybe they're just in the problem set itself. Anyway, moving on to systems of equations. Okay, so let's start with this system here. And by the way, if you have trouble with this, the best way to do these things is to make up an answer first, throw random coefficients into the left-hand side of these equations, and then figure out what that implies with your answer for the right-hand side of the equations. That's a good way, and then you can go practice to make sure that you get the answer you want by the method you choose to use to solve the system of linear equations. That's what I did to make these up in the first place. Okay, so now we're going to start off with this system by using substitution. I will do a couple different methods of solving this one. So, substitution, successive elimination, whatever, they're kind of similar. Okay, so as far as I'm concerned, this problem session. There's more detail in the book and the lectures. Okay, so what we're going to do is we're going to write first x in terms of, let's call this equation 1, 2, and 3, and we're going to write x in terms of y and z using equation 3 just because. So this implies x equals 3y minus 2z plus 2, where we've just put x on one side by itself. Now we're going to plug in here into 1 and 2. Plugging x into these things gives us two different equations. So 1 gives us 2y minus 3z equals negative 5. And 2 gives us 5y minus z equals 7. So let's call this 1 prime and 2 prime. I guess 3 prime, whatever. So the same thing as 3 though. Okay. Now we can solve 1 for y to get y equals 3 halves z minus 5 halves. Now I can plug that y into 2 prime over here to get 15 halves z minus 25 halves minus z equals 7, which implies 13z equals 39, implies z equals 3. That's a nice round number because I set these up the way I just mentioned I did before, by making the answers first. Now I plug 3 into the equation for y to get 9 halves minus 5 halves is 4 halves, or 2. So that implies y equals 2. I plug both those down here. We get 3 times 2 is 6, minus 2 times 3 is 6. That's 6 minus 6 is 0, plus 2 equals 2. So the answer is 2, 2, and 3, using substitution or elimination. And that wasn't too bad. However, we're still going to do this in other methods as well for practice. Next method will be to create a matrix A, which encapsulates the system of linear equations, the left-hand side at least. All we're doing here is writing the coefficients down appropriately, right? So 1, negative 1, negative 1, 1, 2, 1, and negative 1, 3, and negative 2. So there you go. That's A. And here, B, the thing we're trying to make equal to, AX equals B, is going to be negative 3, 9, and negative 2. And the equation is AX equals B. We're going to solve this equation in two different ways. One way is going to be taking the inverse of A. The second way is going to be using Cramer's rule to do this. So first, let's do the inverse method, just because. So how do we do this? Well, first we need the determinant of A. And this is a good practice doing determinants of 3 by 3 matrices. So we're going to expand the first row. Do anywhere we want. In this case, we're going to expand out the first row. So it's 1 times the determinant you get by removing the first row and first column. That's 2 times negative 2 is negative 4. Minus 1 times 3 is 3, so it's minus 3. Then it's the second, you take a second element of the first row, but since it's total odd number of rows and columns, it's the first row, second column is 1 plus 2 equals 3. You're going to be adding a negative number to it, so it's minus negative 1 times what you get by removing the first row and second column, which is 1 times negative 2 is negative 2, minus 1 times negative 1 is plus 1, and finally the last one, here we add it because it's the first row, third column, and 1 plus 3 is 4, which is an even number. Recall that in front of all these elements is this term here, negative 1 to the I plus jth power. So it's plus, so this was plus, minus, plus, they always alternate. And then the determinant of what you get when you remove the first row and the third column is 3 times 1 is 3, minus 2 times negative 1 is minus negative 2 or plus 2. And we're left with negative 13 for the determinant. Okay, that's the first step. Now we need the minors of this matrix. The minors are the determinant of the matrix you get by removing the appropriate row and column corresponding to that element, corresponding to that minor. So we already did the minors for 1, 2, 1, 1, 1, 2, and 1, 3. They're the things in these parentheses. So we have the minor for 1, 1 is negative 7. The minor for 1, 2 is negative 1. And the minor for 1, 3 is 5. That's one here. Now, we need the rest of the minors as well. We continue on doing these mini determinants. The minor for 2, 1 is what you get by taking the second row and first column and getting rid of them. That leaves negative 1 times negative 2. That's 2. Minus negative 1 times 3 is negative 3. So minus negative 3 is plus 3. Equals 5. Next, we have the minor for 2, 2. Remove the second row and second column. Second row and second column. That gives us negative 2. Minus negative 1 times negative 1 is 1, so it's minus 1. That is negative 3. Now we're on M23. Second row, third column gone. That leaves 3 times 1 is 3. Minus negative 1 times negative 1 is 1. So it's minus 1 or 2. Almost there. M31 is third row, first column gone. So it's this one. Negative 1 times, 1 times negative 1 is negative 1. Minus negative 1 times 2 is plus 2. That's going to be 1. M32 equals, M32 equals third row, second column gone. So that is, third row, second column, that's 1 times 1 is 1, minus negative 1 times 1 is plus 1. That equals 2. And finally, the third, 3 times 3, 3. Third row, third column gives us 2 times 1 is 2, minus negative 1 times 1 is minus negative 1 or plus 1, equals 3. We've done it. Now we form the inverse by taking 1 over the determinant, and then taking the matrix we form by taking the transpose of the conjoint matrix, which is the matrix consisting of all these minors plugged in the appropriate spaces with this negative 1 to the I plus j multiplying it. So first we would do this. So first I'll put them in the correct spots. So it's negative 7. This is negative 1 times negative 1 because it's 1. So basically anything that adds to an odd number, you put a negative 1 in front of. So I'm flipping this sign, keep this sign the same. Flip this sign, keep this one the same. Flip this sign, keep keep this one the same, flip this sign, and keep this one the same. Transpose, or negative 1 over, so negative 1/13 times negative 7, negative 5, 1, 1, negative 3, negative 2, 5, negative 2, 3. That's your inverse, A inverse. We want A inverse B will give us X, because AX equals B, so A inverse B equals X. We left multiply both sides by A inverse, as we did in the lectures. That gives us negative 1 over 13. We can go through and do this thing out. It's going to be a vector. I'll give myself some space there. So the first one is the first row dotted with B. That's 21 minus 45 minus 2. That would be 26, negative 26. The second one is the second row dotted with B. That's negative 3 minus 27 plus 4 is also negative 26. And the next one is the third row dotted with the inverse dotted with B, which is negative 15 minus 18 minus 6 is minus 33 minus 39. Divide through, and you get our answer from before, 2, 2, and 3. There we go. We did this the same way. We did the same answer using matrix inversion instead of using substitution/elimination. Now we'll do one more time using Cramer's rule, and be done with this particular example. I don't have room anymore though, so I have to violate my rule and write this over again. Luckily, I have the notes on this, so I can actually write A over again, start from A and B over again, start from there. So here we go. A and B over again. Here's A. 1, negative 1, negative 1, 1, 2, 1, negative 1, 3, negative 2, negative 3, 9, and negative 2. There we go. Now for Cramer's rule, we also need the matrices B1, B2, and B3, which are computed by taking A and replacing the appropriate column with B. So the first matrix is negative 3, negative 1, negative 1, 9, 2, 1, negative 2, 3, negative 2. This is very exciting. B2 equals 1, 1, negative 1, negative 3, negative 1, 9, 1, negative 2, negative 2. And sorry, B2 and B3 equals 1, negative 1, negative 3, 1, 2, 9, negative 1, 3, negative 2. There we go. Okay, so it's B1, B2, and B3, and what we need for each one is the determinant of B over the determinant of A. We already have the determinant of A from the previous thing. That's negative 13. So now we just need the determinants of all the B's. So, determinant of B1, we expand always across the first row to be consistent. So that's negative 3 times negative 4 minus 3. Now we switch the sign here because this is the second term. You're always going to alternate signs. So that's plus negative 18 plus 2. Right? Negative 18 plus minus negative 2 is plus 2. And then that's when we keep the sign. And that's going to be 27 plus 4. Because minus negative 2. So if we add that up, we get negative 7, so that's 21 minus 16, that's minus 31. That is negative 47 plus 21 equals negative 26. Hooray, okay. B2. Again, first row, we get 1 times negative 18, because the 9's there now, plus 2. Plus 2. Then we get special sign here, plus 3, negative 2, plus 1. And then we keep the sign over here, negative 1. That's negative 2 plus 9. We add them all up. We get negative 16 minus 3 minus 7. That equals minus 26 again. Looks good. And then finally, B3, same first row again. That's 1 times negative 4 minus 27. Switch the sign here. Plus 1 times negative 2 plus 9. And then keep the sign over here. Negative 3 times negative 2 plus 9. And that's going to equal negative 31 minus, plus 7 minus 21. That makes negative 52 plus 7 is, wait, did I miss something here? Hold on a second. That's 31, negative 31, plus 7 is negative 24. And then we have, oh, I did miss something, I messed it up over there. That's the third row, so that's 3 plus 2. Yeah, I did it wrong. The last one, remove the first row and the third column, which gives you 3 plus 2 is 5, so it's actually minus 15. So that's minus 46 plus 9 equals negative 39. There we go. Okay, and you divide them all by A, you get 2, 2, and 3 as before, and we're done. That covers using Cramer's rule, and done the same thing using all 3 methods. Okay, hopefully that's some good practice. Now we'll do one last example and finish off this lecture. This one is from the book. This one I'm going to go through, even though I went through it in the solved solutions, because it gives you, I think it's a useful thing to see, and it's a little confusing to go through, and it gives you an idea of what to do when you don't have a fully determined set of equations such that you produce a single unique answer. So here's the system from the book, from the problem in the book. First equation is x1 plus x2 equals 1, and second equation is x1 minus kx2 equals 1. Now the question is, what are the values of k that give you no solution, one solution, and more than one solution? Okay. Now we can deal with this a little bit by moving around the equations by adding the 2 and subtracting the 2. So if we add the 2, we get 2x1 plus 1 minus k x2 equals 2. We subtract them and get rid of the x1s completely, and we get 1 plus k x2 equals 0. Now first consider the second equation. If k equals negative 1, then the left-hand side of the second equation implies 0 equals 0. That gives us the first equation, which gives us, so in that case, if k is negative 1, then you get 2x, the first equation is 2x1 plus 2x2 equals 2, or x1 plus x2 equals 1 is the only equation we have, and there's an infinite number of solutions, so there are infinite number of solutions when k equals negative 1. Any solution that satisfies this equation works. So this is what happens when you have an underdetermined set of equations. You can write one variable in terms of the other, and that's all you can do. And there's an example of this in the problem set. So when k equals negative 1, you have an underdetermined set of equations, because if you notice, when k equals negative 1, you have the exact same equation. Right? When k equals negative 1, you have two equations that both say x1 plus x2 equals 1. So you only have one equation in two unknowns, underdetermined, so all you can do is write one variable in terms of the other one. Okay. Now, what happens if k does not equal negative 1? Then the second equation implies x equals 2. Plugging x equals 2 in the first equation implies x1 equals 1. So it's a single solution. So if if k does not equal negative 1, there is one unique solution, which is x1 equals 1 and x2 equals 0. So that gives you a sense of how this works. When you have an equal number of unique equations and unknowns, of distinct equations and unknowns, you can get a unique solution. When you have more unknowns than unique equations and distinct equations, you get potentially many solutions. And that's your situation in which the equations are contradictory, in which case you get no solutions. So for instance, if we had x1 plus x2 equals 1 and x1 plus x2 equals 0, we have no solutions because they're contradictory equations. If you subtracted the first from the second, you would in fact get, sorry, the second from the first, you would in fact get 0 equals 1, which is not true in most cases. Okay, so there you go. That covers solving systems with linear equations. I hope there's some good practice there. In the next one, we'll finish up on linear algebra with stuff on eigenvalues and eigenvectors and matrix and Markov chains. Thank you very much.